Hey, so this is Joseph, and this is the third part of the third chapter of Stewart's calculus, and we're going to be talking about antiderivatives. So basically, an antiderivative is the opposite of a derivative based on its name. So if you have one function that is the derivative of another function, if you take the antiderivative of that already differentiated function, you'll get the original function again. That's the concept of an antiderivative, and let me write it out in like a little clear of a way here. Alright, there we go, a little bit clearer. So the general symbol for the antiderivative is a capital version of whatever the function name of the beginning function is. So capital F of x is the antiderivative of lowercase f of x if the derivative of capital F of x is equal to that original function for all x. So that means a good example is, remember the relationships between displacement, velocity, and acceleration. So velocity is the derivative of displacement, and acceleration is the derivative of velocity. Well, let's say you have a velocity equation, you want to figure out what the distance equation is. You can take the antiderivative of the velocity equation, and you should be able to get the displacement equation. That's how antiderivatives work, and that's generally how they tend to be helpful. So, for the most part, taking the antiderivative is really just doing the opposite operation to a function as you would should you differentiate it. And given our differentiation formulas, and specifically that with regards to polynomials, it should be pretty intuitive how to go the other way. However, what we need to remember is the derivative of a constant is 0. So because the derivative of a constant is 0, there could be a constant in the antiderivative of a function. We don't know, because sometimes when we take the derivative of a function, there's a constant, sometimes there's not. So that means that every time we take an antiderivative, we've always got to add a plus c to the explicit antiderivative that we take. Every time we write out the antiderivative, we have to tack on a plus c in there just to account for the possibility that there is a constant in that added onto that function. And all that this constant would do is shift this function up or down the y-axis, right? So it doesn't make the shape of the function or the movement of the function terribly different, but it does make values different, and it is important. So we need to add it unless we have constraints on the antiderivative. So let me write out explicitly what the formula for antiderivatives are with regard to polynomials, and you should be able to kind of guess at this. Okay, so here is the differentiation formula right here for polynomials. You take the n down, make that a coefficient, and then you subtract 1 from n. Now, the anti-differentiation formula goes the other way. So what we need to do in this case, to get rid of this, we need to be dividing by something and then adding something. So let's write out the anti-differentiation formula version of this. Alright, so we'll start off with the same. F of x equals a times x to the n, and if we were to get the antiderivative, which is capital F, you'd add 1 to n, and then take that number and put it on the bottom, stick it in the denominator, divide a by that number. And so this would reverse this operation here. So we call f prime of x f now, and we want to get f, which would be the antiderivative. In this case, f is the antiderivative of f prime. We can add 1 to n, so that would just make that n. Divide over here, the n's cancel out, and we come back to ax to the n. Pretty simple, kind of intuitive, and if like this symbolic notation doesn't work out, don't fear, because we will do a sample problem with general antiderivatives like this. And oh yeah, remember the plus c, very important. So this is problem number 4 from page 273 of your book, and the question asks, given this function f, find the antiderivative, the general antiderivative. So we're going to apply that anti-differentiation formula, as it were, to this. So we've got capital F of x equals, and now you got 9, add 1 to that, that's 10. And so then you've got 8 by 10 x to the 10th minus, add 1 to 6, that gives you x to the 7th, and then divide 3 by 7, plus that 3 is going to become a 4, adding 1 to it, 4, and then divide 12 by 4, you make that a 3. And then you have to add a c onto the end, remember, because there could be some constant out here. We don't know. And now, to prove that this anti-differentiation works, let's take f prime of x, alright, and then now we're going to take the derivative. So bring 10 over, you get an 8, x to the 9th, minus, bring the 7 down, you get a 3, x to the 6th. 4, that becomes a 3. Yeah, you bring the 4 down, multiply, that turns into a 12, the x turns into 3, and then the c is a constant. Look, so you get the same thing. Anti-differentiation, you can go both ways. Alright, so if you remember, we had a bunch of different differentiation formulas for a bunch of different kinds of functions, and we're going to get a lot more later anyways. But basically all of them, they apply in reverse to antiderivatives, and the most important one right now that we know is our trig functions. So I'm just going to write out for you the anti-differentiation functions for trig functions. Alright, here we go. So if we've got, these are our little f's, then these will be our big F's. And it's really just the opposite of the differentiation formula. We've got the derivative of sine is cosine, so the antiderivative of cosine is sine. The derivative of cosine is negative sine, so that means the antiderivative of sine is negative cosine. So on and so forth down here. The tricky thing to remember is the negative. Just remember that the derivative of cotangent is negative cosecant squared x. So that means the antiderivative of cosecant squared x is negative cotangent x. Just bring the negative over to the other side. So this is something that's going to be super helpful. You don't really need to memorize, and remember you got the plus c's over here. I wrote that all out just so you wouldn't forget. All you really have to remember is the differentiation formula, and then just think to yourself, alright, I'm taking the antiderivative, what would I need to take the derivative of to get this original function f, and then, write that down for the antiderivative. So, next we're going to do some problems where you take the antiderivative of something and use constraints, and so you can basically solve for this c, and so you're not going to have an unknown shift in your equation. And that's actually probably the most helpful bit of this little section in terms of like physics and stuff, and calculus later on, and just being interesting. Alright, so this is problem 52 on page 274 of your book, and what it asks is, given this expression for velocity, and given that when t equals 4, the displacement is 10, we need to figure out what the displacement equation for this particle is. So, first off, we can figure out the general antiderivative and get an expression for c, and then what we're going to need to do is actually solve for that c using this constraint. So, given this, we need to figure out the antiderivative, and the antiderivative is going to be displacement based on that relationship I showed earlier. So, okay. And remember, we can write this out, that square root, that radical as an exponent. 3/2 t to the 1/2, and that just makes things a little bit easier to think about. So, 1/2, we add 1 to 1/2, and that makes it 3/2. And we need to divide it. And so that would mean that we're multiplying it by multiplying by 2/3 out here. So we'd have 2/3 times 3/2 times t to the 3/2. And so that will all cancel out to be 1, and we just end up getting t to the 3/2, like that. But remember, we've got the little plus c out here. So that is s of t. And what we also have is when t is 4, s is 10. So let's make that t4 right there. And we'd be able to say 10 equals 4 to the 3 halves plus c. And now 4 to the 3 halves is 8. And now this is a really simple equation. We subtract 8 over there. So c is 2. That's what that shift is going to be. And so we can plug it in up to the top to the general equation, and we get the displacement equation is equal to t to the 3 halves plus 2. And there we go. We don't have any unknowns. That's how you do it. So this is the end of chapter 3. It's a really short chapter. I didn't quite go over Newton's method because it's not really relevant on the AP, but if you really want to learn it and it's cool, look back at the linear approximation video I did, which is very similar if you're having trouble with it, and stay tuned for chapter 4. Chapter 4 is where we get into integration, so stay tuned.